Hello everyone. A few kind of review hints and tips for Chem 101. Now, before I get into the nuts and bolts, it's kind of essential you have one of these, okay? So the ACS General Chemistry kind of review guide, okay? Because that's where you're going to essentially practice Chemistry 101 stuff, and it will come back on the Chemistry 102 final. So the Chemistry 102 final features stuff from Chemistry 101 and 102, but all the questions are ACS questions, so familiarity with the book style and the book type of question will be very, very helpful. Okay, all right, so with that out of the way, okay, my advice is, do a rolling review. Start with things, we're going to just talk about some basics in a moment. Try and identify first, where you need help, and practice those the most, right? So if you have a real problem with, I don't know, balancing equations, something like that, I don't know, whatever it is, right? Practice that, right? Okay, and then get good at it, and then move to the next one. So kind of like fill those gaps, plug the holes, right? And eventually, once you've you keep doing that for the first, maybe 6 weeks of the course, you'll be back up to speed. And then it's just, it's almost like throw a dart at the book and just answer questions at that point, and you just, you should be able to answer Chemistry 101 questions kind of at will from the book. Okay, and when you get to that point, that's taken care of, and it will certainly help with your Chemistry 102, particularly the first couple of weeks, because we're doing solutions. Solutions are just a recap of concentration, volume, mole relationships, and that's a 101 topic. All right, so if you want somewhere to start, titrations. Okay, all right. So what I got is the blank. I advise you to obviously print this off, right? Okay, print this off. The links are there at the Canvas site, okay? Print this off, pause me and try questions as necessary. Okay, so first things first, the main kind of focus of chemistry is the mole, right? It's kind of the central concept of chemistry. Chemists, we deal with atoms and molecules, which are tiny, tiny, tiny things, so we don't count them one at a time. No, it'd be stupid, right? It's a bit like an egg, right? An egg's that big. We don't count eggs one at a time, we count them like 12 at a time. We call that a dozen, okay? So if you like, you can count a large number of things more conveniently with a different unit. So 12 things is a dozen. A 6 with 23 0 behind it, that's a reasonable amount of atoms in your hand, right? That's a mole, right? So what is a mole? It's a definition, right? And 1 mole equals 6.02 times 10 to the 23 things. Now, if you got that apples question wrong on the pre-test, you're missing the concept, right? The concept is the mole is just like the dozen, right? You can have a mole of bananas, it doesn't matter, right? It's a mole of things. It's 6 with 23 zeros behind it, things. 1 mole of apples is 6 times 10 to the 23 apples, right? Okay. Typically, we use the molar constant for tiny things because they're easy to count a mole at a time, atoms, molecules, all right? So that's why the mole is so important to chemistry. How is the mole defined? Well, it's defined as 6 times 10 to the 22 things. But if we think about our atomic numbers in the periodic table, hydrogen is 1. What does that mean? It means 1 gram of hydrogen weighs 1 mole, right? But with isotopes, it's actually 1.01, isn't it? Because there's some deuterium out there. So if we specify an isotope and then go with that, so 1 mole is the mass of 12 grams of carbon 12. I should say number of atoms in, which I get it right. So the number of atoms in 12 grams of carbon 12 is defined as a mole, but it's very close to the number in the periodic table, of course. But the number in the periodic table is an average for all isotopes. We just pick an isotope that weighs a certain amount. So 12 grams of carbon 12 is 1 mole of atoms. When's mole day? 10:23. 6:02 a.m. to 6:02 p.m. The mole is so important. It has a birthday and it has has its cake, and it also has a mascot. Genius, right? Mole. All right. Now, simple conversion then. How many oxygen atoms in 1.5 moles? Well, it's a simple converter. So like, 1 mole of O2 equals 6.02 times 10 to the 23 molecules. Now the other weird converter is 1 molecule, because it's O2, equals 2 atoms. All right, so careful, right? So down here. Just move this up so you guys can see it. So 1.5 moles O2 times 1 mole O2 is 6.02 times 10 to the 23 molecules. Some of you would be tempted to press equals at that point, but that'll give you the number of molecules, not the number of atoms, right? There's twice as many atoms. 1 molecule is 2 atoms. Units cancel, all right? Remember, when you do a chain, and pretty much every conversion is a chain, as long as they cancel diagonally, if you remember that, it's going to work, right? The units will work out. And I'll just look at the number 1.8 times 10 to the 24 atoms. Oxygen. 2 sig figs because it's 2 sig figs. Remember significant figures? Hopefully you do. Right. All right, so that's a nice easy one to start. Okay. Moving on. What works for atoms works, of course, for molecules. Okay. So, what's the definition of molar mass? Okay, it's the mass in grams of 1 mole of molecules. Okay. You can also use, well, you know, I'll put an asterisk by that. You can also use it to work out empirical formula weights, right? So technically, molar mass is for molecules, but empirical formula weight is just lumped in there with it. Okay, so if I said to you molecular weight of sodium chloride, molecular weight of ethanol or something, you could work them both out. Okay, all right. So it works for both. All right. Now, how do you find the molecular weight of anything? Well, very simple, right? A molecule is the sum of its parts. You know how much the parts weigh, the atoms, from the periodic table. So you can work out a mass of a molecule in AMU just by adding the masses from the boxes in the periodic table. But remember, those boxes also are the mass of the atoms, a mole of atoms in grams, right? So, hey, a mole of water contains 2 moles of hydrogen and 1 mole of oxygen atoms because it's H2O. All right, so real simple. Use the periodic table. I like to use the phrase a molecule is the sum of its parts. Therefore, add individual masses to get molecular weight. So we do a worked example right now. So what's the molecular weight of CO2? It's C plus O, right? So what's the weight of carbon in the periodic table? 12.01 grams per mole, or AMUs per atom, average, right? 16.0, 16.0, and all that is 44.01 units, grams per mole, if you talk about molar mass, right? Or 44.1 AMU per molecule, if you were looking at a mass spectrum or something, right? Same number, different unit, because of the whole mole thing, right? Okay. Now, hopefully that's a nice review. Now, the relationship, this is something you don't see in the book, but I use it all the time. If you think about, you know, a 3-variable problem, density, right? Density, mass, and volume. I can write it like that, right? Okay. Then if I want an equation, density is mass divided by volume. If I cover up one of the 3, I get the equation to find it, right? Mass is density times volume. Volume is mass over density. You can do the same thing with the molecular weight, just from the definition. Density is mass over volume, that's the definition, right? Molecular weight is grams per mole. If I want to figure out molecular weight, I just take the grams of a sample divided by the moles of a sample. If I want grams, molecular weight times moles. If I want moles, it's grams divided by molecular weight. And I used this triangle when I was navigating that grid when I did slides and ladders in the last one, right? So when I climbed down, I wanted moles, grams divided by molecular weight. I said, hey, divide to go down when I did that grid, okay? Then when I climbed up, I wanted moles, right? Sorry, I wanted grams, molecular weight times moles. So multiply to go up, divide to go down, okay? So very, very simple, very, very simple. Okay, now then this one, last question then. So just use this, like this might be a shortcut for many of you, right? Which is cool, right? Shortcuts are cool. How many moles of carbon dioxide and 27.4 grams of carbon dioxide? Well, I want moles, right? So moles CO2 equals grams of CO2 over molecular weight CO2. So, you know, I could do a chain conversion, which this essentially is, right? But I've just made a kind of a shorter version of it. Grams, 27. If you want to do a chain, you can. over, we set up there, 44.1 grams per mole. Leave the units in because look, they cancel. 1 over something is the something. Let's look at the number on the side here. How many sig figs? 3 there, mole there, so 0.3 sig figs to 3 mole. CO2. Oh, move it up. Ah, okay. Now remember, I've kind of skipped over it, but if you want to try it before I go over it, just pause me, right? Okay, all right. Now, as we go forward, those are the fundamentals, right? So grams to moles, fundamental, right? Working out molecular weight allows you to do grams to moles, right? Okay, and then before that, obviously the definition of a mole. All right, so this all leads into, when combined with balancing chemical equation, quantitative stoichiometry, percent yield and all that, right, which you'll need for organic chemistry, 100%, right? However, before we get to quantitative stoichiometry, percent yields, things like that, we need to remind ourselves how to balance an equation. I gave you one for, I think, diphosphorus pentoxide on the pre-test, right? Okay, but let's talk about this, okay? So, write a balanced equation for the combustion of ethanol. Okay, ethanol, right? So, combustion means you take your organic material. I'll put a 1 there, you don't usually put a 1, but I'll put it. All right. So combustion is adding oxygen, isn't it? So that's alcohol, right? That's oxygen from the air. Now, interesting, when you do a combustion, right, you just add oxygen to all the atoms. So a flame is basically disassembling the fuel into its atoms, carbon, hydrogen, and oxygen in this case, right? But whenever I burn anything, say I burn aluminum, right, I just separate all the aluminum atoms in the metal and add oxygen to them to make aluminum oxide. So you always make an oxide of the atoms in the fuel, right? So if I think about it, I've got carbon in there, its stable oxide is carbon dioxide, so that'll be a product. I've got hydrogen in there, its stable product of combustion adding oxygen is water, right? And oxygen in there just helps it, right? This is why, you go to the gas station and it says may contain 10% ethanol, because it helps it burn better, because it's got some oxygen actually in the fuel, right? Okay, oxygen can't combine with itself, right? So it actually helps with the oxygen from here to burn it, all right? Okay, so there's my unbalanced equation. If you recall, the products of combustion for any organic that contains carbon and hydrogen, right? And sometimes oxygen, all right? Is CO2 and water, because those are the stable oxides of the atoms inside the fuel, right? Now, real simple, what we've got to do. The order of balancing, it's a little trick for an organic, is always the same as the order of the atoms in here, right? So the least first, the most last. So oxygen's everywhere, right? It's hard to balance. Carbon is the lowest number and then hydrogen's the second lowest. So carbon first. One molecule, so we start with a 1 there. One molecule with 2 carbons means I need 2 molecules with 1 carbon. We're balanced with respect to carbon, right? That's what we say. So 2 carbons over here, if you keep track, right? Okay, I need 6 hydrogens. I've got H2O, that's the only place hydrogen appears. 3 2s are 6, right? So now I have 6 hydrogen, 6 hydrogen. All right. Now, think about it. I've locked in 2 of these molecules, 3 of these. So I've locked in a certain amount of oxygen. Count up how many oxygen I've locked in over here. 2 times 2 is 4, 5, 6, 7. So I've got 7 oxygens locked in. I need 7 oxygens over here. Well, there's 1 in there, right? So I need 6 over here, right? So that's 3 times 2. So the answer is 1 ethanol, 3 oxygen, 2 CO2, 3 water. Okay, hopefully that makes sense. And when we balance the chemical equation, it's always the lowest whole numbers in front here. This would be balanced with 2, 6, 4, 6, wouldn't it? But it wouldn't be graded correct because it has to be in the lowest ratio of those numbers. So be careful, when you balance something sometimes, you might not get the lowest ratio. Make sure you just convert it. Okay. Now, slides and ladders, that's my preferred method to do it. Maybe you did, your chains, that's fine, right? Okay, as I mentioned, I prefer a map over a set of directions any day, all right? Okay, so I'll show you how to do a limiting reactant problem, a percent yield problem if you wish, okay? Combining balancing and grams, molecular weight, and mole triangles, right? Okay, so what we got, CO2 is formed from the combustion of 4.05 grams of ethanol, so it's this equation, so let's write that down. First step in any stoichiometric analysis is balanced equation. Okay, fair enough, right? Next, you can straight up do chains. If you want to do that, if you want to do the chains now and then compare my math with your math, you'll find it's the same, okay? But again, it's a technique thing, right? So I'll have to do a grid, grams, molecular weight, and moles. Remember that molecular weight, grams, and moles are related by that little triangle, all right? Make a grid. It's called slides and ladders because we're going to climb up and down ladders and slide across, okay. Now, put in some numbers, right? So we're given 4.05 grams of ethanol. All right, this is the grams row. Our destination is what mass of CO2 is formed. All right. We could also, if you want, work out mass of H2O formed, or in fact mass of oxygen used. Okay, we'll just navigate to these positions, but we're going to go here. Now, grams don't react with grams, right? So I can't just multiply that number by 2 because they're different molecular weights, right? So we have to turn to moles and then convert back to grams. So our journey is climb down. That would be the first fraction in your chain, second fraction, third fraction, very similar to the pretest, right? Now, in order to kind of follow our journey, so we've identified where we start, we've identified where we want to go, so therefore we can identify a journey. We always climb down, slide across, climb up, right? So to do that, grams to moles, we need molecular weight, all right? So I'll just write it in, so it's going to be 2 carbons, 6 hydrogens, 1 oxygen. I'm going to assume you know how to do that, 46 grams per mole. Now, we don't have to fill out all the boxes, right? So if you want to drive to Bolingbrook, you don't need a map of Illinois, right? You just need a map of Will County, right? So I only need this one, but I could fill in this and this if I needed it, right? Okay, but I don't need it, so I'm not going to fill it in. So that's carbon dioxide, we did it before, 44.01 grams per mole. Right? That would be 18, and that would be 32, right? Let's put them in anyway, just for fun, 32 grams per mole. The definition of molecular weight is the mass of 1 mole of the thing, right? So you just look at one formula, not 3, right? Just one formula, that'd be 18. All right. All right. Now, moles is grams divided by molecular weight. That's why it's easy to use the grid, all right? Divided to go down, 0.0880 moles. 1 makes 2, multiply that by 2, all right? That would be another fraction if you did the chain. Twice that is 0.176 moles, and then multiply to go up. Why do I multiply to go up? I want grams, molecular weight times moles. All right, this times this is 7.75 grams. Fair enough. So, check. Now, oftentimes, you'll get like a little add-on question. What volume is CO2? There is no box for volume on here. All you got to remember is 1 mole gas equals 22.4 liters at STP, standard temperature and pressure. So if you ever see standard temperature and pressure in a question, use this converter, right? And its relationship between moles and liters, yeah? So I look at the CO2 moles box, 0.176 moles CO2 times 1 mole is 22.4 liters, which equals, let's write this down, 3.94 liters. All right. All right, so hopefully that's coming back to you. You should be having that kind of, oh yeah, moment. Right? Now, the one often students have a problem with is concentration volume, right? Because the volume of a solution measured in milliliters, like the volume of orange juice or something, right? You go to the store, you buy a liter of orange juice, yeah? That's not the same kind of concept of a liter of gas, is it? Sure, it's in the same space, but one's a solution and one's a gas, right? So be careful, all right? So the equations you use for gases, like 22.4 liters is 1 mole, does not work for solutions, okay? So if you like to think about it, solutions always have the aqueous state symbol, and that's when you'll use moles as CV and all that good stuff from titrations. And this guy here, because I'm talking about gas, right, I look for the gas state symbol, right? I look for the gas state symbol for those kind of problems, right? Okay, so 22.4 liters is 1 mole of gas, right? And then when I talk about solutions, yes, they have a volume in liters, which is similar unit, but different context, right? Okay, so once again, it's a 3-variable problem, right? So if you think about it, concentration is defined as the strength of a solution is how many moles, and we'll see this next week in class, how many moles of solute. So say you're making sugar water, right? So how many moles of sugar are dissolved in a liter of sugar water? So it's the volume of the final solution, okay? All right, so if you think about it, concentration equals moles over volume in liters. That's a 3 variable, so I can do my little concentration is moles per volume thing, right? Oftentimes in lab, you'll record milliliter and milliliter volumes, right? So convert it to liters to get moles, right? So concentration is moles per volume in liters, volume is moles over concentration, but the one we use most of the time is moles is CV. And in the book, you'll see that. You'll see moles equals CV in the book, but it's only one of 3 equations. Occasionally, you'll have to MacGyver another one, right? But if you have this triangle in your head, no MacGyvering, okay? So now, here's a good question, right? So we have, and it could be a flask or something, right? We have 100 milliliters of, now big M means the concentration in moles per liters, that's molarity, right? More about that next week, all right? 6 mole per liter HNO3. I'm going to assume it's exactly 6 moles per liter and we use 3 sig figs, right? Okay, now, question, how many grams? Well, if you remember, and I'll write it up here, yeah, grams, molecular weight is grams per mole. What relates these 2 triangles is moles, right? So if I want to know how many grams of nitric acid is swimming around in there, okay, I can work it out by moles, right? So moles are always kind of the central clearinghouse of any conversion, if that makes sense. So if I want the moles, I'm going to use this equation, right? So moles HNO3, and my destination is grams, right? Moles HNO3 equals concentration times volume, which equals concentration, 6 moles per liter, times, now careful, that's 0.1 liter, right? Which equals 0.6 upper OO mole. All right, so swimming around in there, I got 0.6 moles. Makes sense, right? It's 6 moles per liter strength, and I've got 0.1 of a liter, so it's a tenth of its, you know, number of moles, isn't it, for 1 liter? Okay, so then, hey, moles is grams over molecular weight. Sorry, my mistake. I want grams. Grams equals molecular weight times moles. Molecular weight of HNO3, I'll just look it up, right? So it's 63 grams per mole. Add up the parts, 63 grams per mole times 0.6 equals 37.8 grams. Hopefully, you know, you paused me and tried it. Okay, all right. Fair enough, right? Okay, now the next one is a real test, right? So if you're just carrying along, you know, you're watching this, you know, that makes sense, right? Try this next one because it kind of is a little trickier. It's like a, you know, one of the most common issues students have occasionally is titrations, right? So this is a non-one-to-one titration. So do the slides and ladders thing. Titrations are just slides and ladders with solutions, yeah? You can try doing the weird, in my mind it's weird. You can try doing the chains, that's fine, right? If you're into chains, do it, right? But it's kind of a robotic way to do it. I'm being critical, right? Again, it's like, you know, it's like a procedure you learn and you follow without thinking, right? If you do the map, it's kind of an intuitive thing, right? So I prefer the map, okay? So, you know, pause me right now, try it, I'll come back and I'll show you my way. All right, you're back. Let's read the question. What volume of 12 molar sulfuric acid is needed to completely neutralize 25 grams of sodium hydroxide? It's a slides and ladders with combined, right? So first thing I've got to do, I've got to write a balanced chemical equation. It's acid plus base makes salt plus water. Maybe you remember that. Now, the reason it's weird is because sulfuric acid is diprotic, right? So I'm going to need 1 molecule for 2H plus, yeah? Whereas NaOH is monobasic, so I'm going to need 1 OH per molecule. So I'm going to need twice as many molecules to get the right equivalence, right, for H plus and OH minus. And we'll see that when we balance, yeah? Swap the partners. I'm going to get Na sodium sulfate 2 plus, I like to write water as HOH when I do acid-base titrations because it allows me to keep track of the ions. You can keep track of individual atoms like balancing, you know, but if it's ionic, you can keep track of ions, right? So I've got H plus ions, sulfate ions, sodium plus, OH minus, plus, minus, plus, minus, okay? So let's balance it real quick. I like to balance what looks easiest first. I got 2 sodiums there, 1 there. 2 OHs, 1 OH. So you've got an OH minus and an H plus to make water, right? So 2 H pluses, 2 H pluses, 1 sulfate, 1 sulfate. That's now balanced, okay? All right. So first step of a, you know, quantitative slides and ladders type approach is balancing, right? Quantitative stoichiometry. All right. So now, careful. We want, and it says grams of this guy. So that's a solid. That's going to need grams, molecular weight, and moles to go with it. And this guy's aqueous. That's concentration, volume in moles, right? So I'm going to set up my kind of mixed table here, right? So this guy's aqueous. So it's concentration times volume equals moles. That's that triangle there, okay? So I've used that triangle in my slides and ladders, right? And this guy here, grams divided by molecular weight, is moles because it's a solid, right? Okay, let's start with some numbers. What volume, so that's our destination, what volume of 12 molar, 12 moles per liter, H2SO4 is needed to react 25 grams of sodium hydroxide? Because we know the formula, we can work out the molecular weight, 23 plus 16 plus 1, 40. Okay, so I can plan my journey, right? So I've got to climb down, slide across, and then think about how we get there, right? Okay, it's a bit of a modified thing. So we climb down, 25 grams at 40 grams per mole was 0.625 mole, right? 2 reacts with 1. If you just did a 1-to-1 like you've often done in titration, you get it wrong, right? This is a 2-to-1 ratio, so I'm actually using half as much, 0.313 moles. Makes sense. I need half as much H2SO4 because there's 2 H pluses per molecule, right? This guy only has 1 OH per molecule, so to make OH cancel H plus, I need twice as much as the thing with 1, or if you like, half as much as the thing with 2. All right. Now here, it's not a quick climb to the top because I want to go in the middle, right? But we know, this is why this is so important, right? If I want volume, it's moles over concentration, okay? So volume equals moles over concentration, which equals this number, over 12 moles per liter. This number equals, let me get down to the bottom, 0.026 liters, 26 milliliters. Oftentimes we'll quote the answer in milliliters because it's a titration. Fair enough, right? So hopefully you got 26 milliliters or 0.026 liters if you did it by chains. Again, if you do it by chains, it's just memorizing a procedure, right? When the procedure goes slightly off script, 2-to-1, oh, here it's a bit more intuitive. Okay. Now, real quick, importance of the mole. As I mentioned, the mole, I'm going to pause for a second because I'm running out of time. Okay. All right, so the mole, as I mentioned, is kind of the central clearinghouse of all conversions, okay? And you've kind of seen most of them right now. So if I want to go up to grams of material, molecular weight, grams and moles. Grams are pure substance. In other words, it has to have a formula, right? Because if you don't have a formula, you can't get molecular weight, right? And then down here, it's the classic one, we did it already. Number of particles, 1 mole equals 6.02 times 10 to 23 particles, right? So if you want, you can work, we did this one with the atoms of oxygen, right? You can go from grams to moles to number of particles, right? Or just from moles to number of particles, I think we did. Okay, so you can plan your journey. This is a journey planner, right? Okay. Other ones, we just did it. Concentration is moles per volume in liters. This is for solutions, concentration, volume, moles. All right, and finally, the simpler one we did already. For gases, volume, moles of a gas, 1 mole, 22.4 liters at STP, okay? So you can navigate, say, from a volume of a gas to moles to number of particles. You can work out concentration to moles to grams. We did that with nitric acid a minute ago, okay? So this is a true journey planner, yeah? Everything goes through moles. If you ever get stuck on a conversion, just convert it to moles and then think, where do I go next? Easy. Okay. Little review. I've given you the answers, okay? That's for a reason. Okay, so this is an old Chemistry 101 test, okay? So try and answer the questions without looking at the answers, and you can check the answers, all right? Okay, if you follow through what we did already, it's actually the same one. So the kind of the work's back in there, all right? Now, as I mentioned, ACS, right? So the ACS book, and I kind of stolen a few questions from the Chemistry 101 chapters, right? Okay, so you get this kind of question, right? So what I want you guys to do is kind of try and identify where you're strong, where you're weak, right? And this can kind of help, and what we just did can kind of help. And then the answers are given, right? So you can check your answers. Yeah. All right. Okay. I'll be really impressed if you can do. They're mostly pretty straightforward once you've got the basics, but number 5 is kind of a true test of character, right? I'll be impressed if you can do number 5. If you want to get back to me and ask me how to do it, that's fine. Okay, it's a trick, right? Okay, so it's interesting. On an ACS test, you get literally 70 questions in an hour or something, so it's less than 2 minutes per question. This is designed to kind of test the super student, right? So like most people finish their ACS test and come back to this question, right? Don't sit there staring at it for 5 minutes on a test. All right, it's all about getting as many points as possible in the time, right? Okay, so if you can get that one, great. The answer is correct down here. You can check it, but later, right? That'd be one you'd come back to. All right, stop there. Any questions, discussion, or office hour? Okay, see you next time.